Dear students, under the topic complex analysis, here we have another significant problem on continuity and differentiability. The question is to show that f of z equal to z bar is continuous at the point z equal to 0, but not differentiable at z equal to 0. So first we shall prove the continuity, that is, the given function is continuous at the point z equal to 0, for which we have to prove three conditions, that is limit z tends to z naught of f of z exist. This is the first condition. The second condition is to prove that f of z naught exist, that is the function exists at the point z naught. And the third condition is to prove that this limit which exists will be equal to the function at the point z naught. So if we prove these three conditions, we are done with the continuity of the problem, that is continuity of this function. So now first we shall see what is z naught. In the question z naught is given to be 0. So the value of z naught is 0. So first we shall check the existence of the limit. So limit z tends to z naught, that is z tends to 0 of f of z is equal to limit z tends to 0 of f of z is what? Z bar. So what is z bar? Actually we know that z is equal to x plus iy. Z bar is the conjugate of z, which is equal to x minus iy. And so now the limit also turns in terms of x and y, because as z tends to 0 and z is equal to x plus iy, as z tends to 0, x will tend to 0 and y will tend to 0. So we have written the limit in this form, and z bar is x minus iy. Now we have to choose a path in order to check the existence of this limit. So we are going to choose the path y is equal to mx. So this limit will be further equal to limit. Now since x and y we have written in terms of x, we will have the limits only for x minus I, y is what? Mx. So we can take x in common and we get 1 minus im. So now when we apply the limits, this will turn out to be 0, which implies that the limit exists. So therefore, this implies that limit z tends to z naught of f of z exist. So the first condition of continuity is done. The second condition is we have to check whether f of z naught exists. So what is f of z naught? F of z naught is equal to f of 0. So let us substitute 0 at the place of z naught, that is at the place of z. So what is z actually? X plus iy. So when z is 0, if you substitute it, we get this as 0, since we know that if z is equal to x plus iy and if z is equal to 0, obviously each of this, that is x will be equal to 0 and y will also be equal to 0, and so on the whole when we substitute it becomes 0. So therefore the function becomes 0 at the point z equal to 0. So second condition is also done. The function exists at the point z naught. The third condition is we see that the limit is equal to 0 and the function at the point z naught is also 0, which implies that the third condition is also satisfied, and therefore the function f of z is continuous at the point z equal to 0. So we are done with continuity of the problem, that is continuity of the given function. Next we will check the differentiability. So in order to check the differentiability, we have to show that f dash of z naught exists. And what is this f dash of z naught? It is equal to limit z tends to z naught of f of z minus f of z naught divided by z minus z naught. If this limit exists, then we say that the given function is differentiable at the point z naught. So this is equal to limit, what is z naught in our question? It is equal to 0. So limit z tends to 0. What is f of z? F of z is z bar. So that we will write. So z bar minus f of z naught. But f of z naught is 0. So we need not write that. Divided by z minus z naught is z. Because z naught is 0. So This is equal to we are going to change it in x and y. So x tends to 0, y tends to 0. And what is z bar? X minus iy. And what is z? It is x plus iy. So this is what we obtain. Now we have to choose a path along y equal to mx so that we can check whether this limit exists or not. So now we choose a path y equal to mx. So what happens to f of z naught, f dash of z naught? This will be equal to limit. We will have only x tends to 0 because we have changed y in terms of x. And x minus I. What is y? It is mx divided by x plus I mx. So this is equal to limit x tends to 0, x is common in the numerator, so 1 minus im divided by x multiplied with 1 plus im, and we see that this x and x gets cancelled and we are left out with limit x tends to 0, 1 minus im divided by 1 plus im. And we clearly understand that the value of this limit depends on the value of m. So the value of the limit depends on m. So as m keeps on changing, the value of this limit also changes. Because you can check that when m is 1, what is the value of this limit? 1 minus I divided by 1 plus I. What about m equal to 2? If you take m as 2 over here, 1 minus 2i divided by 1 plus 2i. So we see that the value of the limit keeps on changing as the value of m changes. Therefore, the limit is not unique. So if this limit is not unique, this f dash of z naught does not exist. So f dash of z naught does not exist. So if this does not exist, then the function f is not differentiable. That is, the function f of z is not differentiable at z equal to 0. So therefore we have proved the second part also. So I hope you would have understood both the problems, that is the problem which we have seen in our previous video lecture on the same topic, and this problem, which is a very significant problem in the examination point of view. Thank you.